Welcome to everybody. This is the last AJS of the year. The series of the next year will start on October 8th. I have to recall you that this AJS will be recorded and then posted online. I think there are no problems. Today we have Paolo Ventura that will talk about a full description of Benjamin Feir instability of Stokes waves in deep water.
Thank you all for coming to the fight. Today I will present you this result that Professor Massimiliano Berti and Dr. Masper and I developed during last year. I would classify it as a simple mixture of simple and trivial things. And of course you can guess what my part in that is. But nonetheless, I will try to explain what we accomplished. As the title suggests, this is an instability result for the water wave system, but I will mainly focus on the linear algebra tools we developed to obtain a solution instead of the physical source of the problem. Now, let me present you what the subject of instability are, namely the Stokes waves, which are equilibria of the struggling water wave system, which is this what you can think it as an ordinary pseudo-differential system, where the pseudo-differential part comes from the Richtein-Neumann operator, G eta, which I will not describe here because of lack of time. But the Stokes waves are this kind of equilibrium. And in dynamical system, when you have an equilibrium, what you do is to linearize the system to be at this equilibrium, and then you find eigenvalues of the linearized operator. Because when you find an eigenvalue with a positive real part, you can build a solution which grows exponentially in time. And so in this case, you say that the system is linearly unstable. A classic result in bifurcation theory is the proof of existence of a unique one-parameter family of Stokes waves. The parameter epsilon is the amplitude of the Stokes wave, and is the first of the two parameters that will guide the entire Benjamin Feir problem. The second one steps in because we don't look for instability of the water waves perturbed with coperiodic perturbations, but instead with 2 pi over mu periodic perturbations, which are called very keenly long-wave perturbation because they have a long period. And in 1967, Benjamin Feir discovered by experiments that small amplitude Stokes wave are unstable when perturbed by a long wave. For a rigorous proof, we have to wait 30 years, almost 30 years. And the first one is by Bridge and Milke, which proved Benjamin Feir instability in finite depth. And they use a method of Hamiltonian center manifold theory to prove this result. But this method won't work for infinite depth case. For this case, the solution arrived last year by Louis and Strauss, which proved that the Benjamin Feir instability happens also in the infinite depth case. But both the proofs have in common to restrict the parameter mu to a small epsilon-dependent neighborhood of 0. And this is not the case for numerical and physical simulations, which can do more than that. In fact, as you see, in 2010, De Koning and Oliveras showed this picture of the eigenvalues of the Benjamin Feir, of the water wave linearized system at epsilon fixed, different from 0, and mu variable. And they depict this figure 8 in the complex plane. And this is exactly what we were able to prove. We proved that the linearized system yields to eigenvalues that, after cubic remainders, have this form. Of course, at the end of the presentation, I will give you the actual form of the 2 eigenvalues, but for the moment, let me show you how they depict the 8. They stay at the origin for every value of epsilon when mu is turned off. Then, as soon as we turn on mu, they suddenly branch off into the two imaginary, non-trivial apart half planes. And then, eventually, they collide again on the imaginary axis to split again, but this time on the imaginary axis. And that, by Hamiltonian motivations, excludes new kinds of instability in this regime. So we have proved this figure 8. Now, okay. After this little introduction, let me explain mathematically the problem. We, as I said, are looking for eigenvalues of the linearized operator. So we linearize the system, and this is a classic way to do this kind of things. We linearize the system, and then there is a suitable change of variables that puts the system into this form. You see that it is a linear system, and the linear operator that guides the equation is given by this pseudo-differential operator with a matrix symbol. The functions p epsilon and a epsilon are even, analytic, and we can provide a Taylor expansion at whatever order we want for them, of course, with increasing effort for any order. For our case, we just needed, I think, the second order expansion of a epsilon and b epsilon. The Benjamin Feir instability comes from the eigenvalue 0 of this operator, which has at epsilon different from 0 for some features of the starting operator. It has algebraic multiplicity 4 and geometric multiplicity 2. But when epsilon is 0, the geometric multiplicity steadily increases to 3, and we can give explicitly a basis of the kernel, which is given by the first, the second, and the fourth vectors here, and extend it to a basis of the generalized kernel by adding this F0 plus. I give you this basis, I show you this basis because it is the starting seed of our construction. We start, as we will see, we start from this basis and we will build a basis for the perturbed operator. As I said, we are looking for long wave perturbations, and these kind of problems are brilliantly solved by Block-Decoupling theory. For my purposes, I will just give you this result, that the spectrum of a pseudo-differential operator with matrix entries, matrix symbol, whose entries depend 2π periodic over the space variables, splits into the spectrum when acting on L2 of R, that you may think as very, very extremely long wave perturbations. It is given by this union of spectra of shifted operators and epsilon, which act on 2π periodic functions. And so in this way we transform a continuous spectrum into a union of discrete ones. Of course, a union depending on a continuous parameter. But there is also Block-Decoupling theory for 2πn periodic perturbations, which gives a discrete union of discrete family of unions. Okay, and another feature that Block-Decoupling theory provides is the symbol for the shift operator L mu epsilon, which is given just by translating the momentum variables of the imaginary unit times mu. So you see here that we started, okay, I didn't emphasize on this fact, but we started from a Hamiltonian operator, a real Hamiltonian operator, and we find here a linear complex Hamiltonian operator, which is given by a Poisson tensor times a self-adjoint complex matrix. This is the first feature of our operator L mu epsilon, which gives in particular a lot of properties, but in particular the fact that no instability can arise by perturbing a simple, purely imaginary, isolated eigenvalue. Because, okay, I will see you this. Picture the situation. You have the complex plane, and you start from a single eigenvalue. Now, by that result, when a Hamiltonian operator has an eigenvalue with non-trivially apart, it has a counterpart in the specular half. Now, if our single eigenvalue branches off into one of the two imaginary, non-purely imaginary half planes, suddenly its counterpart appears. And this would violate, of course, the continuity of the spectrum or the multiplicity of the eigenvalue. But in Benjamin Feir phenomenon, we branch the eigenvalues off from the origin, which, as I said before, has algebraic multiplicity 4. In particular, the 8th figure, when we start from this, that for multiplicity eigenvalue 0 is given by 2 eigenvalues, which branch speculatively in the two half planes. And then there are 2 other eigenvalues with, that will remain purely imaginary. And these 2 eigenvalues will be eventually the figure 8. And of course, when we take mu negative, they will be the other part of the 8. And this is the first feature of our operator. The second one is that it is complex reversible, which, apart from the technical definitions, helped us a lot because reduces the degrees of freedom of the problem. Now that I gave you the ingredients of the recipe, let me say something about how we reached our solution and the novelty core of our proof. The first one is that we give a symplectic version of Cato's perturbation theory. What is the fact? That you should keep in mind that eigenvalues, even for a 2 times 2 matrix, do not depend analytically on the parameters, even if the matrix centers do. That's because also in 2 times 2 matrix you have to take square roots or something similar. And so the Cato's idea is to not follow the eigenvalues, but instead follow the region of the complex plane where you think the eigenvalues are localized. So the point is that we, say this. Okay, we consider the half plane, the complex plane. We know that our eigenvalues will start from 0 and will be near 0 at a certain moment. And so we take a loop gamma that encircles the origin, and we consider this projector P mu epsilon. The range of P mu epsilon is exactly the direct sum of the generalized eigenspaces of the eigenvalues which lie here, encircled by gamma. And this is not the only feature of P mu epsilon, because it is not just a projector, but it is the projector, in the sense that in classic Cato's theory, you consider operator L, which is a self-adjoint, and P is the orthogonal projector on the invariant subspace. In our theory, we consider a Hamiltonian operator, and hence P is a skew Hamiltonian, which means that it satisfies this identity here. And this is what one wants from a projector in symplectic theory. Okay, and Cato theories doesn't stop here. Let me pause. Okay, too much. Cato theory provides a symplectic isomorphism, symplectic in our case, but in general it is an orthogonal isomorphism, when you consider L as self-adjoint. In our case, instead, we consider L as Hamiltonian, it gives a symplectic isomorphism between the starting subspace and the final one. And so we have a basis of the starting generalized kernel, and we can construct in this way a basis for the perturbed invariant subspace we are considering. And this basis, because of the properties of this operator U, which come from the properties of the projector P, this basis is symplectic and reversible. And of course, symplectic and reversible are what you want from a basis when you're studying a symplectic and reversible operator. So we expand the basis, and this is not just a Taylor expansion, it's more than that, to find the basis of the new invariant subspace. As I said, this is not just a Taylor expansion, it contains more information, because you see that, for example, when you turn off mu, you find a real basis, and this is indeed a good thing, because you know that L epsilon, L epsilon is a real operator, while L mu epsilon was complex. And so at mu turned off, you want a real basis to study the operator. So this is the basis, and once we have a basis, we can reduce our problem from infinite dimensions to a 4-dimensional problem. And we can represent our operator restricted on the invariant subspace to a 4 times 4 matrix, which will be a Hamiltonian and reversible matrix. Namely, L will be given by this product of two matrices, where J4 will be very simple, and B is self-adjoint. And we give a Taylor expansion for the matrix B. The point here is that we observed that the top left block, 2 times 2 block of the matrix L, given by the matrix J2 times FE, it already presents the Benjamin Feir phenomenon, in the sense that you compute its eigenvalues and they depict a figure 8. So what one could think to do at first when you have a 4 times 4 matrix is to compute the characteristic polynomial and find the eigenvalues, but this is not the right thing to do, because we want to not perturb this top left block that already shows Benjamin Feir instability. Hence, what we do is to block diagonalize the 4 times 4 matrix into a diagonal 2 times 2 block. So 4 times 4, but with 2 times 2 diagonal blocks. The first thing we have done was to find a symplectic way to put L0 epsilon, which has this very simple form, into its Jordan form. And of course, you can think like in 2 minutes of a way to do this, not symplectic, but the point here is to do it symplectically, and it's not so simple. Well, it is, but it was not our first idea. And then we extend this symplectic conjugation to the case when mu is turned on, and we find a new Hamiltonian reversible matrix L1, which will be practically unchanged, apart from the fact that the off-diagonal 2 times 2 block will have this pure 0 at this entry. And okay, this the point of doing this first block decoupling is to have the off-diagonal blocks to not depend on the sole parameter epsilon. They will depend always to mu times epsilon or to mu left alone. And this is the first thing to do. And then a more serious kind of block decoupling is given by this one, the second one, which is achieved by a conjugation with an exponential of a Hamiltonian matrix, which gives a symplectic matrix. And what we do here is to apply the expansion, and then we consider the homological equation to eliminate this first part of diagonal blocks with this Lie brackets. And this is possible because at the end of the story, because of these two diagonal blocks have disjoint spectra. Because the Sylvester equation here, this is called the Sylvester equation, can be solved exactly when the two matrices D1 and D0 have disjoint spectra. And this is the case in our considerations because the spectrum of the first, the top left block is given by entries which expand like mu, and the other block just has two eigenvalues which depend on the square root of mu. So yes, they are disjoint, and we solve the Sylvester equation by explicitly inverting the matrix, the 4 times 4 matrix, which is associated to the linear system, which is at the end of the story, the Sylvester equation. We thought about other ways to solve the Sylvester equation. The way is more complicated than that, but at the end, the simpler way is the best one. So you have a linear system, a 4 times 4 linear system. You just take the matrix, invert it, and you arrive at the solution. And then we have the new conjugation. But the other fact is that we can think of repeating this infinity many times to achieve the completed Block-Decoupling of the matrix. And this is indeed what we do by the implicit function theorem. So we look for another conjugation that keys totally the off-diagonal blocks of the matrix and renders the L operator just as a completely diagonal, block diagonal. As I said, this is possible because of the implicit function theorem that we apply to this equivalent system, which is not this infinite idea, but it is kind of clever, because you will have that your perturbation on the diagonal block will be given explicitly once you find the conjugation matrix S. And the conjugation matrix S will satisfy a very simple implicit equation. So there is no more to do here, because also the linearization of this implicit equation is given exactly by the linear operator associated with the linearization is exactly up to remainder terms the same of the previous stuff. And so we already inverted it, and so we just use it again and prove that solution S exists. And with this, we find the block diagonalized matrix, which will have a first block which gives instability, and the second block which is stable, because I told you that the second block will give these two eigenvalues which stay on the imaginary axis, and the first block will give these two eigenvalues which branch off into the out of the imaginary axis. We give the Taylor expansion of the two times 2 blocks, and then we can compute the eigenvalues of the two blocks. And as I said before, now I can give you the real expansion of the two unstable eigenvalues. One of them is unstable because it has a positive real part, and the other one is just given by the Hamiltonian properties of the matrix. While the other two eigenvalues of the stable block are purely imaginary. And as I said, this pair of eigenvalues depict this figure 8 as we expected. What's next? Well, one can try to prove the nonlinear instability, starting from this linear instability result. Then one can think of other collisions of eigenvalues of the operator L mu at 0, which are classified by a theorem. And then a third thing that one can think is that Benjamin Feir instability appears in many dynamical systems. And so the question now is, what they have in common? What is this, the subtle thing under Benjamin Feir instability? Okay, thank you for your attention.
Thank you, Paolo. Are there any questions?
I just wanted to know the physical observations of the phenomenon, because I cannot imagine how to observe this.
I expected this question, but I did not prepare the answer. And
A picture from Google.
yeah, there are some movies, not movies, but there are some videos on YouTube about Benjamin Feir instability, and you see that they start perturbing these steady waves, and then at a certain point a jerk wave starts, and it just gives a strange phenomenon.
Are there any questions? If not, we can thank again, Paolo. And see you in the